All right, good afternoon. Welcome back to our session, the rest of the session on HUBzero applications and experiences. Next up, we have Lan Zhao from Purdue University, and she'll be talking to us about delivering climate data to a broad user community through GeoShare. In fact, the rest of the talks in this session will all be about GeoShare, so we'll be learning a lot. Welcome to Lan.
Thank you. Can you hear me? Very good. Okay. So next I will talk about a HUBzero tool we developed for the GeoShare project. The tool's name is called CMIP5 Data Aggregator. This is a tool that we use to help a broad user community to access the climate model output generated by the CMIP5 project. So this is our team. We have two small groups, one from Purdue University that includes Jay Wuxin, Carol Song, Steve Clark, and me. We are responsible for software development and operation and user support. And then Nelson Viloria, he's an agricultural economist. He used to be at Purdue, now he's at Kansas State University. He is mostly responsible for driving the design of this tool based on the input from the community, and also later to engage the users for testing and getting feedbacks. First, I want to give you a quick overview about the GeoShare project. GeoShare stands for Geospatial Open Source Hosting for Agricultural Resource and Environmental Data for Discovery and Decision Making. So in this project, we try to develop a cyber infrastructure that can provide a large global geospatial database for agricultural, natural resource, and environmental research. And then on top of this database, which is freely available, we also provide a series of data analysis and modeling tools and the training programs that can directly utilize the data. The system has been developed using a HUBzero platform, and it's available at geoshareproject.org. The screenshot on the slide shows how the project is organized. There's a central node at Purdue that's hosting the GeoShare cyber infrastructure, and there are 5 data nodes that's distributed across the globe. So the CMIP5 data aggregator tool was developed was one of the tools we developed for this GeoShare project. CMIP stands for Coupled Model Intercomparison Project. This is a large coordinated effort among the international climate modeling community. The goal is to develop a framework for climate model comparison and diagnosis, validation, as well as to data dissemination. It's established 20 years ago by the Working Group on Coupled Modeling and the World Climate Research Program. Currently, it's at phase 5, so we call it CMIP5, and it has generated a lot of data. And the data has been used to generate the 5th assessment report for IPCC, which is the organization who assess the climate change of the Earth and its impact for social and economic systems. Currently, the data are available to the public, and it's mostly through the Earth System Grid data portal. There's a web page listed on the slides that shows how to access the data. Although the data has been made available to the public, a large group of scientists who want to use the data and for their research actually has encountered all kinds of problems. So on this slide, it's a blog posted by a professor of international sustainable development at UC Berkeley. So in his open letter, he said, "Dear climate people, I'm an economist. I'm interested in projecting the impact of climate change on human and natural system. And then, you know, what's a huge pain in the neck for all of us, trying to get the model output into a format that is usable by someone without at least a computer science undergrad degree. While you make a big deal out of having all of your climate model output in a public repository, we do not have the skills to read your terabytes and terabytes of NetCDF files into MacBooks and put them into a format we can use. So essentially, he's addressing a common problem that's faced by a large number of social scientists and economists who are interested to use the climate output to study the impact of climate change. So why the data is so hard to use? It's mostly because the size of data is huge. There are more than 2 million gigabytes of data. And typically for scientists who wants to use the data, they need to first locate the specific data they are interested in among all these big piles of data. And then they need to download the data typically to their local system. And then after that, they need to do a lot of processing. For example, they need to convert the data into the right spatial and temporal resolution. They need to convert the data into the right format. They need to extract the variable information they need. So at the end, they also need a lot of storage space while they are processing this data. So all of this requires specialized skills and high-end computation resource. So this is not just a problem for those social scientists and economists who are considered to be the non-expert for climate modeling. Actually, there's a survey in 2014 that's among the IPCC Working Group 1. Those are the experts for climate modeling. And this report revealed that more than 60% of these experts also encountered a lot of problems when facing processing the large data associated with the climate model output, and also have trouble to get timely access to the model result. So all of this motivated us to develop this CMIP5 data aggregator tool. This is a HUBzero tool. It's deployed and running on GeoShare and its goal is to help those economists who want to run model simulations to study the impact of climate change. And currently, this tool allows users to either directly download the CMIP5 model output data, or they can compute the growing season measures of specific climate variables and using a flexible spatial aggregation scheme. I want to highlight several main features of our tool. First, it has a very easy-to-use interface that can help users easily select the data they want to access. And then it integrates the Globus Online service at the backend, which essentially provides fast and reliable data transfer service. And then it has several R scripts that can aggregate the climate model output to any user-defined levels. It also allows users to convert the aggregation result into maps for visualization purpose. Last but not least, all the data processing histories are tracked automatically and then converted to metadata. So they are associated with the data and available for download. And this is a workflow diagram that shows how the tool works. On the left-hand side, the user select a combination of climate variable, the GCM model, our RCP pathway condition, and then the tool will use Globus Online to download the data from the remote CMIP5 archive. The data will be stored on the hub as a series of NetCDF files. At this time, user can either download the data to their local system directly, or they can continue to aggregate the data. The tool provides some default regional map files, regional weight files, and a growing season average file for maize. And user can also upload their own regional map files and regional weight file if they want to have their own calculation done. And the last step is to convert the aggregated result into maps. And then the map can be downloaded for publication purpose or just for documentation. This table shows the data coverage through the data aggregator tool. Currently, user can access the climate output generated using 5 global climate models as listed in the first column under 4 representative concentration pathways as shown in the second column. And then we have the data for growing seasons for a number of crops that's shown in the last column. A little bit more about the data source used by our tool. This tool connects to a remote CMIP5 model output online archive that's provided by the ISI MIP project. That's another project focused on climate model comparison. And the data is processed from the original CMIP5 data into monthly means and interpolated into 0.5 degree resolution. And we have the climate variables for average, minimum, and maximum surface air temperature and precipitation. And the data is organized into NetCDF4 format, and it's typically aggregated into 5 to 10 year slices. And we have the data for 1960 to 2099. So we integrated GABBS Online to enable fast data transfer. If you haven't heard of it, GABBS Online is a fast, reliable, and secure data transfer service developed by the GABBS project from the Argonne National Lab and the University of Chicago. And our integration work includes 2 parts. First, we set up a GABBS Connect endpoint on the hub server, and then configured that to connect to the remote CMIP5 archive. And the second part we did is to create a service wrapper for the GABBS client commands, and then make it available within the workspace so that tools can invoke it to start the file transfer. And the syntax is very simple. It's just a submit ISI MIP transfer. And then by providing different command line options, the tool can either browse the files from the remote system, or they can just request specific files to be transferred. And this has worked very well for our tool. And although it's currently hard-coded, but it should be very easy to extend this so that other tools can leverage this work and then use this service. Another important work done by this project is to support spatial and temporal aggregation for geospatial data. For spatial aggregation, right now we support any arbitrary spatial aggregation as long as the user provides a regional map that map each grid cell to an aggregated region. And then for temporal, we currently support growing season-based aggregation, which means that we only use the data that falls into the months of the growing season. And that sounds very simple, but implementation is not very straightforward because the growing season actually changes from location to location. As shown on the slide, in the Midwest region of the United States, the growing season starts around May and ends in September. And then in Argentina, it typically starts in October of the previous year and then ends in April of the second year. So the tool has to take that into consideration. And these slides give you an example about what kind of data aggregation is done by the tool. So on the left-hand side, it's a NetCDF file downloaded from the remote repository, and it has a monthly maximum surface air temperature data from 2031 to 2040. It's generated using the IPSL CM5A LR climate model and under the RCP 6P0 condition, and then it's interpolated and bias corrected. So this data is in a binary format. It has 120 bands with 1 band for each month. And then at the right-hand side are the aggregation result for one specific aggregation that's performed by the tool. So it's aggregated into 10 individual ASCII text files with 1 file for each year. And then the data has been aggregated from the pixel level to country level. And that's actually what most of the economic models expect to use. So next I will quickly show you what the tool looks like. This is what you see when you first launch the tool. It has 3 tabs. The first one is download, which is shown here. And it has 3 columns. So the users can select 1 variable, 1 GCM model, and 1 RCP pathway. After that, when they click on fetch data, the tool will invoke GLOBUS online commands at the back end to fetch the data from the repository. And in this case, there will be 10 NextCDF files downloaded to the local system. By local, I mean the hub server. And the user can choose to download the data now or with the metadata attached, or they can proceed to the second step where they can perform different types of aggregation. So on this screen, user can select a climate data they have downloaded, and then they can either use the default regional map provided by the tool, or they can upload their own map. And then they can choose whether they want to do growing season average, and then they can choose different summary statistics. Once that's done, the tool will run some R scripts and then generate the aggregation result. And user, again, can download them now or with metadata, or they can go to the last step where we generate maps. So in this case, there are 10 years of data, so we generate 10 maps. And all of them can be downloaded. So currently, this tool has been released just a few days ago. Its URL is listed on the slide. We still need to add more documentation about this tool so that people who want to run their own aggregation knows what the tool expects, the data format, for example. And then in the long run, we are thinking of using this tool to help drive the development work for GABBS, which is a project Carol Song has presented in the morning, which is a National Science Foundation funded project to develop geospatial data analysis building blocks for HUBzero. We're thinking this specific tool can help drive the development for building blocks related to GLOBUS online data transfer, related to geospatial data aggregation, and also for model output publication and sharing, as well as geospatial data-driven modeling workflows. And this is the last slide, shows acknowledgement for the funding sources. And that's the end.
Very good. Questions for Lan? Yeah.
What was the interface?
It's a Java tool.
And then deployed it as a tool?
Yes, it's a tool running inside the workspace. And we are developing the building blocks for from the GABBS project to help enable some mapping modules that can be used inside Java tools. So right now we are still displaying just a static map at the last step, but in the future we will be able to display interactive maps, for example.